And next up, we've got a double slits question involving sound waves. Now, I say double slits, you don't actually need any slits if you're using sound waves. Instead, you have two speakers that are playing coherent sound waves, and these act as our two wave sources. Okay, so have a go at this question. Okay, so you may recognise this question. We've done part of this question already. In this bit, we're being told, if we remember, that we've got two waves, wave S and wave T, arriving at the point P. And so we're asked, first of all, are the two waves coherent? Say if they are and explain how you know. So yes, they are coherent for the first mark. Second mark, because the phase difference is constant. And if we don't have to write this for the mark, but if we just look here, we can see that the phase difference is half a wave. And wherever we look on this diagram, one wave is half a wavelength different to the other one. Next, we're asked to work out the frequency and wavelength of the sound waves. Well, we get the time period from the graph, that is 3 milliseconds. So we first work out the frequency and then we work out the wavelength. Okay, and now it gets really interesting. So the question then says, the sound waves shown are emitted from the loudspeakers labelled S and T in the diagram, and they're detected by a microphone that's at the point P. Calculate the distance that speaker S must be moved towards P to bring the two waves into phase at P. Okay, so we said that our waves currently, as they are at the moment, the waves are arriving at P and they're exactly half a wavelength out. So that's a phase difference of pi radians. That means that if they're half a wavelength out, we need to move S half a wavelength forwards and then they'll arrive exactly in phase. So the first mark here is for saying we need to move it half a wavelength forwards, and the second one is for dividing this number by 2 to get the distance itself. Okay, and we're still not done, so the last bit is describe how the intensity of the sound wave detected at P varies as we move the speaker from here to where we said we were going to move it to. Now, as it is at the moment, our two waves are arriving at P exactly out of phase. Now, we added these up in a previous part of the question. Let's just do that again quickly now. I'll draw it on the bottom one. So here we've got 0 plus 0 is 0, minus 3 plus 2 is minus 1, 0 plus 0 is 0, 3 plus minus 2 is plus 1, 0 plus 0 is 0. And so this is the resultant wave that's actually arriving at P at the moment where the speakers are now. And this will be a minimum because these two waves are exactly half a wavelength out. And then when they are exactly in phase, the wave arriving at P will be a maximum. So for this last part of the question, we're going to say that at the start, the signal at P is a minimum, and then it's going to increase until when S is in phase with T, then it will be a maximum.